Okay, hello and good afternoon. Sorry for the delay. Let's get started. We were talking about operating systems, what they are, what they do. And the next question is, why are they challenging and interesting? Excuse me. Okay, so if you look at what is going on today in the world of technology, this is a graph that summarizes what happened in every minute of every day of 2021, and there are some interesting numbers to look. The ones that are kind of like pandemic related, there's like 856 minutes of webinar. So basically 856 Zoom hosting per minute per day. Although I thought that would be more, but anyhow, there is 100K Teams users, for example, interacting with Teams every minute. There were 20 million images basically shared through Instagram. If I'm not mistaken, people send images. It doesn't say Instagram. Oh, Instagram. I don't see. Oh, Instagram. It was 665K. Anyhow, you get the idea. 5.7 million search queries per minute. And what is actually amazing about this is that in the heart of today's data center architecture resides operating systems, and without operating systems, none of this would have been possible. Now, in a series of slides, we're going to walk through the shift in technology and to basically look at the trends, and then see how that affects us as operating system designers. So the number of transistors in our chips, in our multiprocessor chips, is doubling every year. And that's basically the Moore's law. This is what you can see here in this graph. We have been having more and more and more transistors in our chips. For a while, until around 2005, we were able to improve the performance of our processors, basically keeping pace with the number of transistors. But what happened around 2005 was that we saw this curve plateaued somehow. So the performance, which is kind of like related to the frequency of the processors, kind of plateaued and stopped improving with the same pace that it was doing before. And the main reason for that was that we hit the power wall. So what happened was, as we were getting our transistors smaller and smaller, we were able to tame the power consumption of our transistors. So for the same power budget, we were able to put more and more transistors and then keep them at high frequency, increase their frequency. But at some point, when we started increasing their performance and decreasing their size, the power started blowing up. And we kind of got to a state where if we wanted to keep up with the frequency, we would have had to put really powerful heat sinks to get the heat that is generated by these transistors, and that was not possible. So as a result, we stopped making them faster, or we didn't stop because we wanted to, but we were forced to stop making them faster. When that happened, the response from architecture community was, okay, I will just put more cores in the chip. So this is around the time where we started seeing a growth in the number of processors per chip. So up to around this time, usually the systems were having like a single CPU, but then they started having a lot. Unfortunately, this didn't this didn't work out well. I have started coughing, but this time I have my hot tea here to help me out. Okay, so this didn't help much because we really didn't address the power problem. We kind of like just took a backdoor of some sort. We added processors, but we aren't able to turn them on, all of them at the same time, and run them at the highest frequency that is possible for them. Because if we do so, then the same thing happens. Our chips are going to melt because it creates a lot of heat. So basically, this didn't help. This is around the time that architects started thinking, okay, this is not working, so what should we do? And the trend that you actually see now is a specialized hardware, something like Google TPUs. So this is a tensor processor unit. This is a processor that is very good at matrix multiplication. So it's a specialized hardware that is designed only for a specific task, which is kind of vector or matrix multiplication. And it does that pretty efficiently, meaning that it gets really high performance with low power consumption. Now you can compare that with our general GPUs. The difference is a GPU can do, it's a general purpose. It can do a lot of things, and it has to do all of those things well. Whereas TPU is only designed to do a specific thing, and it's designed to do that specific thing in a really good way. So very recently, you probably have heard of like something like the Mac M1. This is a continuation of that specialized hardware finding its way to mainstream. You see all these new GPUs. You see all these new. They kind of like are hardware specialized for machine learning applications. So somebody was joking back then that we should expect to see a processor for Firefox. We should expect a processor for Thunderbird. We should expect to have a processor for Microsoft Word. That's definitely a joke, but the point is we have started seeing this shift in this is real. We can't get around power wall. So we still have a lot of demand for performance. So what should we do? And the response is usually, as we've seen in these days, is to come up with a specialized hardware. Now, you know, a company like Apple makes M1 chips, and everybody sees it, and they have this advantage that they're also designing an operating system for that chip. So not everybody has that advantage to design their own chip and then design an operating system for it. So that's one of the things that I was mentioning in the introduction, that in this the era of a specialized hardware, really we have to rethink how we're dealing with ever increasing complexity and the interesting new designs that are coming up every day. In the past, we had only a handful of processors as the computing units of our systems. Now we have our processors are computing units, our GPUs are computing units, our TPUs are computing units, our FPGAs are computing units. Nowadays, your network card, like these small smart NIC cards, have processing units on them. So it requires a new design, and that's, I think, it's a golden time for operating system designers to look at this and then come up with interesting solutions. So I'm going to jump on this. This is kind of like showing how performance plateaued as we got closer and closer to hitting the power wall. And this one is kind of like showcasing a modern processor with many cores. Right now I have one of these processors for my, not one actually. So I have 2 servers. Each one of them has 2 sockets powered by EPYC 7H12. Each one of them has 64 cores. So in total, each server has 128 cores. And this is physical cores. So if you look at the hyper-threading, it's going to be twice as that. So we talked about processors. Let's also talk about memory, and then we'll look at the trends. So when you're looking at memory, memory has different types, and usually you're looking at memory hierarchy. So at the top of this hierarchy, we have the registers. So these are small, so it's very low capacity, but absolutely fast. So access time to registers is phenomenally fast. And then at the bottom of this, you have remote secondary storage, like some remote file system. Let's say maybe you can think about cloud-based storage systems. So there you have huge amounts of capacity, huge capacities, but then really fast access times. So here at the bottom, larger but slower. So overall, cheaper per byte. At the top, you have a smaller units, but then a lot faster. So these are costlier per byte. These are some of the numbers. This is from 2009, so things might have changed a little bit, but usually the order or the ratio remains constant. So that's usually the case. So if you want to access your first level cache, L1, it takes 0.5 nanosecond. To access your next level, L2 cache, that's almost twice. Sorry, almost 20 times more. Excuse me. So that, or maybe that's 10, and then that's like 12, 13 times more. And then if you want to go to main memory, then that takes 100 nanoseconds. So as you can see, there are orders of magnitude difference in the response time as we move into the hierarchy. Now, in this figure, I'm showing you the trend in DRAM bandwidth. Compare that to network bandwidth, and then compare that to SSD bandwidth. So this is kind of new reality that I/O is getting faster and faster. So there was a time where I/O was really slow. So it really didn't matter how you manage I/O. Really didn't matter because they were slow. So you had a lot of time to manage them the way you wanted to do it. It was really important how you manage your CPU, because your CPU was really fast compared to other components. So you really wanted to utilize your CPU the best way you could. But this is changing actually. So as I/O is getting better and better and better, and the performance is improving, people have started looking and rethinking about how to manage I/O. Like all these new PCIe protocols and really huge bandwidth that they provide have forced architects to, I'm sorry, but both like at this point I'm talking about operating system architects to rethink about how we manage I/O. The other thing to note is here is the trend for DRAM. Similar to processor speed, it's also kind of a slowing down. And as you can see, there is this gap between between I/O and memory is increasing. Now, one thing I have to point out is that in this figure, don't think that I/O is faster than memory, because here memory is gigabytes, whereas networking and SSD, they are megabytes, right? So still memory is a lot faster than I/O, but it's kind of like I/O is catching up. So I/O is just the bandwidth is improving and improving and improving, whereas the CPU kind of performance and frequency and your DRAM have slowed down. So we're expecting them at some point to catch up. So the I/O might actually catch up with memory. So I will answer the questions that I'm getting. So just I'm gonna finish these lectures and then come back and answer the questions. Okay, the other trend that we have to look at is basically how users are interacting with electronics. So, or computers. So back in then, you had these huge buildings that hosted computers, and there was just one computer for an entire population of people. Right now, we're at the point where each one of us usually carries around, tens of computers. Your cell phone, your watch, your laptop, your tablet, you name it, right? It's kind of like an Internet of Things. And we came a long way actually to get there. But what has made it interesting, or what makes it interesting in today's age, is that it's not like just the Internet of Things. We also have these big data centers like Google data center or Amazon data center, where it's kind of like a big warehouse. You can think of it as a warehouse scale computer. That's what Google calls their data center. It's kind of like a big warehouse scale computer. And the users of it are basically people. So we kind of carried over this model that we had in a different context. So at the same time, and then like here you have like, let's say lab PCs that we have. They have to deal with a bunch of, users, or ECE cluster. It's not like a, Google data center that has to service millions of requests from millions of users, but it has like, hundreds or thousands of users connecting to it. So our operating systems have to deal with this wide range of use cases, really to keep up with the demand that exists today. So I'm actually going to move on from this slide. I have a similar slide. I'll come back to it in the next lecture. So I'm going to move on from that one. Let's look at the complexity of our operating system. So this one kind of shows the number of lines of code from kernel. This is Linux kernel version 2.6 all the way to version 4.19. And as you can see, then it's kind of linearly increasing the number of lines of codes that we're putting in the kernel. And that's actually one of the reasons that I'm kind of urging you guys to change this mindset that, oh, we have Linux and Linux is working. I will share with you a lecture on whether or not Linux is working, but this kind of shows you that it's probably not working the way we want it to work. The Linux is getting bigger and bigger as time passes by and as we have newer technologies. But with this comes also bugs. So if you have a constant percentage of bug per lines of code, as the size of your kernel increases, the amount of bugs that you should expect your kernel to have also increases. And it might be a time to really wake up to this reality that we need to rethink how we are designing operating systems for our modern computers. So to put all of this together, we looked at the trends in hardware, processors, I/O, memory. We looked at the size of the operating system. We kind of know we're computer engineers, so we sort of know what kind of applications we're running. So if somebody, from mainstream Firefox, Word, Thunderbird stuff to the new machine learning applications that these big giant companies are running, from embedded software like a self-driving car, from different virtual machines, different containers, to you name it, like face recognition, streaming softwares. So every day there are new types of software, new types of requirements, new applications coming up, new hardware is coming up. And then we're in this weird position that we're sitting between a world that is evolving, which is software, and another world that is evolving very fast, that is hardware. And we kind of have to mask these two from each other. So the software shouldn't see the changes in hardware, and the hardware kind of should be kept from the software. Although somebody was saying, because the operating system is not doing its job, these days you see computer architects go and talk to software programmers directly. So they now you have like something like TPU is just designed to do TPU, and usually they don't have any operating system, and that's bad actually. So coming back to what I was saying, so yeah, we are in this weird position that we have to tame this complexity. We have to create this abstraction. We have to mask all these complexities from each other, and we have to be stable. We don't want to design an operating system that we have to then rewrite everything every time a new hardware is added, or have to change the basics of our operating system if a new software type comes up. So that's what makes it challenging to basically tame this complexity. And hopefully during this term, you will get to know the concepts of operating systems, so that this task that looks very scary and complex hopefully is less scary and less complex, and you kind of know how to deal with all these complexities. Okay, while I'm answering the questions, let me download OS concepts. Okay, so let me go and answer some of these questions. Sorry for that. Let me. Okay, so I have 3 questions here. Will we talk about quantum computers in this course? Unfortunately not. I wish we could. It's another very interesting topic that is getting a lot of attention, at least in computer architecture community. I yet to see, I have seen, computer architecture attention. I have seen programming languages attention. I yet to see any attention from, I might be like, I'm not claiming that there is none. I'm just saying I haven't seen, but unfortunately not. So we're not going to cover quantum computers in this course. So it says for slide 62, Numbers everybody should know will be tested on these numbers. Should we memorize them? Even if you were to be tested, the quizzes are open source, so you don't need to memorize. So you can just come to this slide. For the final, no, you don't need to. What are the implementations of I/O caching up to memory? Oh, implications of I/O catching up to memory. Sorry, I just read a totally different thing. So the implication of that is that the I/O no longer should be considered as a not important component. Now, it's really important to also efficiently use I/O and efficiently schedule I/O. In fact, one of my own students is working on this area of scheduling I/O. So again, in the past, you might have seen really brute force kind of treatment of I/O. It didn't really matter, but now that I/O is catching up, they're becoming important again. So we have to really efficiently schedule them. Okay, so let's move on to OS concepts. What we're going to see is basically a brief history of operating systems, and then we'll jump into 4 fundamental OS concepts. So what are those 4? There is threads. I'm assuming you know everything about threads, and you know how to create threads. You run threads. You should know PThreads very well from 252. So if you don't, go refresh your memory. I'm not going to talk about the basics of threads. I actually talked about it in SE 350 because those guys haven't taken 252. So if you want, you can watch the lectures, ECE lectures today. I talked about threads to refresh your memory. If not, you can just go back to your 252 slides and refresh your memory. Then we'll talk about address space. Again, you should know about them, but this is probably another take on physical and virtual memory. There is processes. Again, I'm assuming that you know them, so I'm going to just introduce them. And then bulk of the discussions that we'll have is around dual mode operations and protection. So this last one basically takes most of our time in OS concepts. So let's talk briefly about the history of operating systems. So there was a time where there was no operating systems. This is basically serial processing. So there was this the computer that you would go and sit behind, and this is actually after those big rooms that hosted one computer. So this is like kind of modern computers. But even these, they really didn't have an operating system. So your program would be punched on these punch cards. And then you kind of had these devices. This is kind of like a where you would code. So you would put your card there and start punching your program. Then you would get your punch card and then wrap it around these drums, and this is where this drum would go, and then this drum would start rotating, and there was a head that would read all these holes in the card and then would encode them and do what you wanted. Now, these systems didn't have an operating system, and let's say you wanted to run something C++ or whatever language that was available at that time. So you would have to, before loading your program, you would have to load the compiler. So you would have to grab the cards for the compiler program and load it in memory. Then you would have to kind of like save what the loaded program was, and then you would have to load the linker, and then eventually you would have to put your own program and then let it execute, right? So very painstaking job, time consuming, not fun at all. And then there were just like physical switches. You know, if something would go wrong, the computer would start, you know, flashing a red flash. So that's pretty much what before operating systems we had, the height of technology before operating systems, and that wasn't efficient. So then started the time started where we had operating systems, and actually the evolution of operating systems happened really fast. Within 10 to 20 years, we started having to see the, you know, the kind of operating systems that we're seeing now. The first breed of operating systems were simple batch operating systems. So these are the operating systems where you would batch a bunch of programs together and run them in a batch. Now, you probably wanted to have them all be in the same language so that you don't need to, you know, load the compiler and loader every time you switch between jobs. So you would have a bunch of jobs, all of them written in the same language, all of them using the same compiler, the same loader, the same linker. And then this basically improved throughput. So we started getting really good throughput compared to the previous one where each user would come and sit and do their own compiler, do their own loader, and then, you know, all that hassle. Now we kind of batch everything. We submit the batch, and there was this program called Monitor, which kind of like is the grandparent of operating systems today, and that would you know, schedule the next program one after another. Now this improved the throughput, but it was really still lacking I/O support, in a sense that not lacking I/O support, but not doing it efficiently when it came to I/O. The reason was, let's say you were running program 1 and program 1 needed I/O, then it would go to I/O, and now the program has to wait. So does every other program that comes next, because I'm not going to switch to another program. So because I have a batch of jobs and I do one at a time. Now, if one job wants to wait, then everybody else has to wait as well. Now, this was not a good idea. So soon after, we started having multi-programming batch operating systems. So these are like kind of like an improvement to the simple batch, where if one process goes for I/O, then the monitor would pick another process and run that other process. And if this process goes to I/O, then you probably could come back to the first process that you were running. So this improved the CPU utilization. Now we're utilizing CPU better. So in the first one, we might actually have job to run, but we're not using the CPU to run that job. We're just waiting. So CPU cycles are wasted. In this one, we just switch to another program immediately if one of the programs have to wait for I/O. But the response time was bad. The reason is, let's say you're program 1 and you need to print F something on the screen. So, and that's I/O. So the moment you issue the printf, you're gonna be swapped by another process because we want to just keep running, right? So now you're out, another program starts running. Now this other program, you don't know how long it takes for it to finish. Maybe this is kind of like a day worth of computation without any I/O. So now you have to sit out and wait for this program to finish. So your response times really is bad. So you're kind of like get stuck again, and you get really bad response times. To fix this, soon after multi-programming batch operating systems, we started seeing time-sharing operating systems, which kind of sticks around even now. Now, I mean, things have been added. Even this time-sharing operating systems use this multi-programming paradigm, but these time-sharing operating systems focus on bringing response time to what is acceptable for users. So what does that mean? It basically means that I'm going to cut the CPU time into a small time quanta, and then I'm going to share this time quanta between users. Let's say I have one CPU, and then I have hundreds of jobs to run. I can just give job one a couple of microseconds on the CPU, then interrupt, go to the next one, give it another 100, give it another 100 to the next one, and next one, and next one, and next one, and then come back. This way, you basically get to use the CPU every time interval, like depending on what the size of this time quanta, this time quantum is, and depending on how many jobs I'm serving, you're guaranteed to run on the CPU every fixed amount of time, right? Depending on, again, time quantum, size, and the number of programs that I'm running, and that gives a better response time. It's kind of like your program is making progress, right? And again, that's something that has remained. Now I'm going to jump over this. A quick archaeology of operating systems, and this meme actually makes a lot of sense because I'm not going to spend much time talking about this. I have included links on the course website for those of you who are interested. So the first link, the IBM 026 key punch, is a link that talks in more details about the serial processing and specifically about IBM 026. Then there are two really informative talks on YouTube. These two. One is about the first Unix operating system, and the second one is a history of BSD. And then this link, SOSP history. Basically, SOSP is a prominent conference for operating systems, and in 2015 they had a history day. If you follow the link, you can see a lot of resources about the operating system archaeology, if you're really interested. Okay, moving on. Now, in the rest of the lecture, we're going to go through these four fundamental operating system concepts, as I said: threads, address spaces, processes, and dual mode operation. Before doing that, though, let's talk about how our systems boot up. And I think this is kind of like interesting for many of you probably to know what happens under the hood when you turn on your computer. How is the operating system brought up? So the first step in, and by the way, this is just an example. It's not, different systems might have different processes, procedures to bring up the system, but this gives you an idea, right? They're not that different. So you probably will find something being replaced with something else, but still the flow looks kind of the same. So this is mostly for x86 system. So in an x86 system, you usually have your BIOS being booted on a ROM. This is a read-only memory, and it's usually called boot ROM. And so a ROM is an expensive piece of hardware that is very slow to write to. So if you want to write something to ROM, it's going to take a long time. But if you want to read from a ROM, it's going to be super fast, super fast. So you usually put your BIOS there. Then what does this BIOS do? When you turn on your computer, the BIOS runs, and it has only one job. And its job is to bring the bootloader from disk. So usually the bootloader is at some address in disk, let's say address 0 to address like, I'm just making it up, to address 128. So you just read this and then bring it to memory. And once you bring it to the memory, the BIOS just jumps to the first instruction of the bootloader. And then the bootloader goes and grabs the kernel and brings it to the memory. Once the entire, not entire, but then enough of kernel is loaded, then the bootloader jumps to the first instruction of OS kernel. And from there, the operating system brings up a bunch of processes, create a bunch of processes, and probably one of the early ones that allow you to then start using the system is the login process. You probably remember from ECE 252, you have the init process, then you have a bunch of other processes, and eventually you create the login process where the user then can put in their username and password and start using the system. Now, let's just, for practice, ask some questions. Why didn't we use the ROM to just put the entire kernel? So why did we need 3 levels of indirection? Why did we need the BIOS and then bootloader and then kernel? Why couldn't we just put the kernel in our BIOS, in our boot ROM, and just start with kernel? So to answer that question, there are many reasons. So I'm going to just mention 1 or 2. One of the obvious ones is, well, the ROM is really hard to write to. And kernels, you keep updating your kernel, as you have seen, probably Ubuntu, Linux systems, Mac OS, Windows. You keep, doing updates. So that would be really hard to do on a ROM. Another reason that you might think of is basically ROMs are expensive. So when we were talking about BIOS, we were talking about a few bytes of code. When you're talking about kernel code, you're probably talking about, a couple of hundreds of megabytes of code. And putting that big of a ROM over there is going to just be too expensive. And again, there are other reasons that you might think of and make sense why we don't put kernel in the ROM. Now, next question to be asked is, okay, you convinced me not to put my kernel in BIOS. Why do I need the bootloader? For that also, there are a couple of answers. The first one, what if you have multiple operating systems? Like, what if you have a system that has Windows and Linux? So which one should the BIOS grab? If it grabs Linux, then you can't go to Windows. If it grabs Windows, then you can't go to Linux. That's probably you want to bring bootloader, who would then see, oh, there are 2 operating systems to choose from. So I'm going to ask the user which one you want, and then they can choose which operating systems they want, and then the bootloader can go and grab it. The other reason is, when I was talking about BIOS and bootloader, I told you that it's kind of the bootloader, we put it from address 0 to 128. I think maybe it's 256. I don't exactly remember, but it's very small, and it's from 0 to something. So BIOS can go and read raw bytes, put them in memory, and then jump to it to execute them. And that's fine. But operating system has a lot of files, right? An operating system is huge. It has a lot of files. And it doesn't really sit in consecutive addresses, consecutive bytes of your disk. So you have a bunch of files here, maybe from address X to Y, and then a bunch of files here from address Z to W, and another bunch of files address K to J, whatever. So, and how do you know where each file is? Well, that's the job of the file system. The file system knows that this file is divided between this kind of bytes over there and these bytes over here, and another, consecutive bytes over there. And this is the job of the file system. Now, the file system is part of operating system, and it's actually big, and you need a lot of code to interpret, to know how the file system works. And, having that in BIOS is hard to do anything with file system. Whereas bootloader is generally speaking longer. We have more flexibility. We can put a couple of file system functionality in bootloader so that the bootloader can find initial files for an operating system. If you remember, it was the init process. It knows where it is and it can go and grab it and so on and so forth. So that's another reason why BIOS first brings bootloader and then bootloader goes and looks at the files and brings operating systems. Okay, so now that we kind of know how to bring up our computer, let's see what happens next. Now the operating system comes up, what does it do? So the operating system, the bottom line of operating system is to run programs. Now the life cycle of programs, somebody writes them, edits them, finalizes them, and then you compile it. After you compile your code, you create this executable image that has data and the instructions to be executed. Now, at some point, you want to execute this. So at this point, the operating system loads your executable image to the memory. So in this box, I have the memory. So your instructions and data come in. Now, operating system allocates some extra memory for you, in particular, the stack and heap. So now you have everything ready to start executing. The moment operating system wants to allow you to start executing, all it does, so up here is memory. Down here, I have the processor. And the processor has bunch of registers. One of the most important ones is the PC, the program counter. So the operating system, all it has to do is to make this program counter point to the first instruction of your code. And that's it. And then what does PC mean? PC means what is the next instruction to be executed. So the moment PC points to an instruction in your program, next cycle, that instruction is going to be executed. So that's kind of like transferring control to your program. Operating system has to do a bunch of things. First, to set up the memory footprint of your process. And then eventually the last step is to set the PC and then switch mode, which is the topic of discussion in this lecture. And then that's it. You start running your program. Now, if you dig deeper in what happens in executing a program, so here I have that figure again. So there's the instructions, there's the data. My PC is pointing to an instruction. I'm going to read that instruction. So I'm going to go to memory, read that instruction, and then I have to decode that instruction to see what that instruction is. Am I going to add 2 registers? Am I going to multiply 2 registers? Am I going to divide the value into registers? Or am I going to write to memory? Is it a load instruction? Is it a store instruction? Is it a jump instruction? Is it so all the instructions that you know? So I'm going to decode them. Once I decode, then I'm going to execute that instruction. So typically that's done in ALU, right? So if it is an add, you're going to get 2 of your registers, add them, write the result back to your registers. And if it is, let's say, a store, then you're going to get 1 of your registers and then write it to memory. Or if it is load, you're going to get 1 of the memory bytes and bring it to your registers, right? So that's where you execute. And once that's all is done, then I'm going to update PC with the new PC. So is it like, am I going to be running the next instruction in the sequence? Or am I going to jump to another function? Am I going to, is it like a loop? So I have to go up, do all the computation again. So let's look at it as a black box that says, okay, what is the next instruction? And that's how I update PC. Now, a very important fact that sometimes gets missed that I want to emphasize here is how important is it to access memory fast? So what a slow memory access means for executing a program. And to answer that, you have to know how many times you go to memory when you're executing your program. And the answer to that is at least one time per instruction. So for every single instruction, we're going to access memory or memory hierarchy. Let's put it that way, because we're going to add a lot of caches to cache this to speed it up. But the point is, I'm going to go to memory at least once. If I'm doing like load and store, then once to just see if it is a load or a store, and then another access to write or read from or to memory. So accessing memory hierarchy in a fast way is in utmost importance for us. Because if that's a slow, the entire execution will be slow. So in the second part of the course, so after the reading week, we will be looking at address translation. And that there we focus a lot on how we can speed up the access to memory so that we get good performance. And then we see what compromises people have made in doing so, and what security risks now our systems are facing because of those decisions. So I'm just setting that discussion up probably a month and a half sooner, but just keep this in mind. We'll come back to this later. I got a question I'll definitely answer once we are. I guess I think it's a good place to stop and answer the question. Okay, so the question I got is, for a load and store, does the operating system get involved, or does it just execute on the hardware? That's a really good question. And the answer is, it depends, right? So before the operating system, so some of the things that I kind of glossed over here is that operating system doesn't just bring your program here. Operating system tells the hardware that this is the memory region that you can touch. So it kind of like puts a boundary on what memory region you can access. Now, if you issue load and store, hardware checks to see if you're within this boundary. And if you are, hardware just executes that instruction. If you want to access anything other than what you're allowed to, then hardware goes and wakes up operating system. So hardware preempts you, goes to the operating system and says, oh, operating system, this guy is accessing this memory. What should I do? And the answer to what should I do is sometimes terminate. It's illegal. It's segmentation fault. Sometimes the answer is, oh, okay, so I missed it. I have to allocate some more memory to this guy. Maybe like you do your stack wants to grow. So your allocated stack is here. Now your stack wants to grow, and you're not allowed, for example, to access this memory region. Now, if you do, hardware is going to ask operating system, is this allowed? And operating system is going to say, oh yeah, I'm going to let me allocate. Operating system allocates some memory, updates your boundaries, and then goes back to the hardware, says, yeah, now execute it again. So it's kind of like a coordination between hardware and operating system, how accessing memory works. And a lot on this in the second half of the course. So good question, though. Okay, we saw all of this. Next, let's jump into the first operating system concept, and that is the notion of thread. Just a reminder, you should know all of this. Thread is short for a thread of execution. So it's pretty much a sequence of instructions that we execute on a CPU that are executable. Now, threads have state. They have some local variables. For instance, their execution state, their context, their execution stack, their local variables, their priorities, their what process they belong to, how much time they have gotten on CPU, you name it. So depending on different systems, you might have different things for your threads to store. And as you can remember, a multi-threaded program has more than one thread, and these threads can dynamically create more threads. So initially you start with the main thread in your process, and then that main thread can spawn other threads, and so on and so forth. Again, another reminder of the POSIX thread library, PThread. So you probably have seen it and coded with it. The PThread create, exit, PThread join, PThread yield. These are the kind of functions that you probably have already programmed with. Again, if you don't remember, definitely go back and refresh your memory. Another recall, the life cycle of threads. So kind of like when you create your thread, it's in an initial state while it's being created. Once it's actually created, it becomes ready. Actually, give me a second. Let me see if I don't think. Okay. I thought I updated this slide, but okay, it's fine. Okay, so when your thread gets scheduled, its state becomes running. If your thread yields, the state becomes ready back. If your thread joins on a bunch of children, you go to waiting. If that event that you're waiting for happens, you come back to ready, right? And then eventually you're done. This cycle could happen again and again. Also, this cycle could happen again and again. And then there are, oh, this we have it, never mind. But then from ready to finish and from waiting to finish, these are also possible. Let's say, the main thread calls exit, and then all the threads, no matter where they are, they're running, they're ready, or they're waiting, they all terminate. So again, this should be familiar to you. Could you go over execution stack? Could you go over execution stack? Yes, I actually will touch on execution stack. We have slides on that, so don't worry, it will come up. If I don't answer your question, then ask it again. Okay, so what operating system usually keeps for threads is called thread control block. You probably are familiar with PCB, which is the process control block. Operating systems usually have TCBs as well. So this is the thread control block, and it basically has the information about the thread. So what is the unique ID of the thread? Where is the stack for a particular thread, what program counter this thread is at right now, what is the state of it, is it running, is it waiting, is it ready, what are the values of the registers for this thread, and usually a pointer to the PCB of the process that this thread belongs to. So that's also stored in TCB, and so much more. So this depends on what you want. Like, as I said, you could keep other information like the priority of the thread. You could keep some metadata, like how long this thread has been running, and so on and so forth. So it's not limited to these. It usually includes these and then much more. Okay, the second concept is address space. Now, what is an address space? So address space has two components. The first component is set of accessible addresses. So set of addresses, let's say address 1, 2, 3, 4, 5, n. So the addresses themselves, and also what we have in those addresses. So these are like addresses of each byte. What do I have stored in byte 0? What do I have in byte 1? What do I have in byte 2? What do I have stored in byte n? So a combination of these two form address space. So the addresses and their values. Now, there are two types of memory address space that we're interested in. There is the physical memory, so which is basically the data storage medium in your computer. So if you have a computer with 4 GB of memory, then your physical address space is a combination of 2 to 32 addresses from 0 to 232 bytes you have addressable, and then whatever you have stored in your physical memory, that becomes your physical address space. The address to physical memory and the values that are stored in your physical memory. We also have virtual address space. So virtual address space is different from physical address space, obviously. And it's usually dictated by the length of the bus in the computer. So if you have a 32-bit system, then you have 2 to 32 bits, 2 to 32 bytes that you can address. With 32 bits, you can address 2 to 32 different addresses. If you have a 64-bit system, then you can address 2 to 64 different bytes. As you can see, in a 64-bit system, which is usually our systems today, like my laptop is a 64-bit x86 system, and your PC, most of the systems have moved to a 64-bit system. The size of virtual address space the virtual address space has more bytes than the physical address space, right? So the physical address space, you're limited to your physical memory. Now you have 4 GB or 8 GB, or like in exceptionally fast systems, 32 GB system physical memory. You have 32 GB of physical memory, but your virtual address space is huge. You have a lot more bytes per process in virtual memory than you have in physical memory. Now, you usually don't have only one process running in your system. You have hundreds of processes running, and each one of them has its own virtual address space. So each process that you're running has 2 to 64 bytes of virtual address, and you're probably running hundreds of them. But then at the end of the day, you kind of have limited physical memory. That's where the job of operating system as an illusionist comes. And also, it's a combination of illusionist and a referee, because we have limited hardware that we want to allocate to these processes, that each one of them thinks that they have 2 to 64 bytes of memory, whereas in reality, probably I have 2 to 33 or 34 bytes available. So this is where we map virtual address to physical address. So this is the mapping that is done by the operating system. It says, okay, I'm going to map, these virtual addresses for process 1 to these physical addresses in my computer, in the system. And then I'm going to map this range of virtual addresses in process 2 to this other physical address region in my physical memory. So this mapping between virtual memories and physical memory is done by the operating system. And again, this is a topic of the second portion of the course, where we talk about address translation. So meaningfully, we want to translate virtual addresses to physical addresses, because each process basically speaks in the language of its own virtual memory. And then the system works with a limited physical memory, so we have to translate from this virtual address language to this actual physical address language. And this is memory address translation, which, again, as I said, is a topic of the second half of the course that we will talk about. And as I mentioned, we want this to be super fast. So we don't want this translation to take a lot of time, because we're accessing memory at least once for every single instruction. So for every single instruction, I have to do at least one address translation. And if these address translations are slow, then my entire system will be slow. Okay, so this is a typical C program that you might have. Oh, somebody asked a question that I think is appropriate to answer now. So somebody asked, in our lab 1, do we deal with virtual address or physical address? And the answer is that you're dealing with physical address. Usually in real-time and embedded systems, we get rid of this address translation altogether, because as you will see, it slows down the system. And sometimes it's actually not predictable what happens when you are translating addresses. So some real-time embedded systems just forgo virtual address translation, and they just stick to physical address. So everybody uses physical address, which is the case in our lab. So everybody has access to physical memory, right? It's not secure because everybody can, go and destroy kernel, for example. There's no isolation. But again, let's say you have a satellite and you're designing an operating system for a satellite. You're writing the operating system and you're also writing the programs yourself. So there is a trust that programs are not going to go and distort memory. So anyhow, so for your labs, we're not touching virtual memory stuff. So that I hope answered the question. Could you explain what you mean by translating virtual address memory to physical? Does that mean you take the content from virtual and place it to physical? No. It means that you have so as I said, the memory that your process sees has 2 to 64 bytes. So your process can address anything from byte 0 to byte 264. And another process can do the same. They can address from 0 to 264. Another process can access from 0 to 264. Now, the 0 address in process 1 is mapped to address X in physical memory. The 0 address in process 2 is mapped to X prime in physical memory. And the 0 address in process 3 is mapped to address Y in physical memory. So we have a mapping from virtual memory addresses to physical memory addresses. So we have to translate when your process comes and says load address X, they're talking in the language of their virtual address space. They want their byte X in their own virtual address space. Now, in reality, that value is stored in physical memory, and it doesn't necessarily have the same address in the virtual memory. It could be anywhere in the physical memory. So that's where the mapping happens, from virtual addresses to physical addresses. And that's where you do the translation. So you translate addresses to just find where each byte resides. Okay. Okay, I have 6 more minutes. So, okay, let's continue. Now, I'm going to show you how virtual address space layout is that looks like in a usual C program. These bytes, so that your code usually goes here. So this is the binary code for the program. Like this is the bytes of the program, right? The first include is here, all the instructions, the binary code resides from address 000 to some address. That's your code. Then any variables, any global variable that you initialize. So sorry, it's actually just the ones that you initialize. So like y equals 15. They go to this initialized data. So your instructions are here, your initialized data is here. What else? So if you have variables that you haven't initialized, like x here, they go after the initialized data. So uninitialized data resides there. Then you have inside your program, if you do malloc, it comes in your heap, which is on top of the uninitialized data. Anything that you have in your main, the environment and the command line arguments go to the top of your address space. And then anything inside your functions, all the variables for your functions are in your stack. So the stack starts from higher addresses and grows towards 0. So you as your stack grows, this is something to note in your labs. So a stack grows backwards. So as the stack grows, you're decreasing the address. Whereas as your heap grows, you're increasing the address. So you're going upwards for heap, you're going downwards for stack. And again, this is the layout of each program in its virtual address space. So I have this like from address 000 to address FFFF. These are in virtual addresses. So this doesn't tell you where my stack is in physical memory. This only tells you where my stack is in my own virtual memory. Now, the mapping happens from my virtual memory to actual physical memory. Oh, I forgot. So if you have these shared libraries that you're including, they usually get assigned in between your stack and heap. So they get virtual addresses in this free region. So operating systems give you that they assign basically a range of virtual addresses to all these libraries that you're using. Oh, somebody is asking, in ECE 150, we were taught that binary code is at the top and stack grows upwards and heap grows downwards. Which one is correct? So, a good question. So, for ECE 350, binary starts at the bottom, and stack grows downwards, heap grows upward. That's the most important thing that you need to know for ECE 350. I hope that answers the question. It's really a convention, right? How do you start from higher addresses and go back to lower addresses, or you start from lower addresses and go to? It's kind of like a convention. Another question that is asked is, what happens when the virtual memory required exceeds the amount of available physical memory? That's what you saw in ECE 252. So you probably saw swapping. You will have to swap. Oh, okay, let's put it this way. It actually happens a lot where the virtual memory that you need is more than the physical memory that you have. And when that happens, the performance really becomes terrible because you will start paging. What happens is that you have to put it in disk and then bring something back from disk and do this and that. So usually you want to use as much memory as you have at most with your physical memory, because otherwise the operating system starts paging it, meaning it kicks out something from memory, it stores it in disk, and then brings something from disk to memory. So, which is time consuming. And I'm pretty sure that you have seen similar concepts in 252, where I think in that context you saw paging happening on processes where you swap out a process and then later on swap it in. But it could also happen for if you have only one process and this process has a lot of memory, then you still can have this where each page of the process has to go to the memory and then come back. Okay, so I think it's a good point to stop here. Let me answer this question and then end the lecture. So the question is there a particular reason why the shared libraries are stored between the stack and heap? Why wouldn't it be stored between the command line arguments and the top of the stack? Yes, so one of the reasons is when you have shared libraries, usually the operating system doesn't give them, assign them any address until you use a function in that library. So you might actually look at this code here. So I'm not using anything from stdio. So it could well be that I have it only here, but I'm not using it. So it doesn't get anything. So these are usually dynamically linked. So if I put it here, I will have to really do all the libraries that I potentially might need from the beginning. I have to allocate them memory or virtual memory, but I may not need them at all. So because they are dynamically linked, then they come here. So because that's where dynamic things happen, right? I don't want to allocate memory to a library that I'm not using from the beginning. And again, putting it here will be constraining because you definitely need to start your stack. So you will have to allocate everything here and then start your stack, which is not a good idea. That was a good question. So somebody's asking, is the virtual address space copied exactly like this onto the memory, physical memory? And the answer is absolutely not. So that would be not a good thing to do. Although we will talk about address translation. In some systems, in early systems that was the case, but not in modern systems. So usually, I think I have a picture of that, if I'm not mistaken. It's usually it's kind of like this, right? So it's this is kind of like a mapping where you map you know, the stack of this guy somewhere in physical memory, and then you map the code of this one here. So you kind of, these are called pages. You page them, and then you divide your physical address space as a page, and then you start mapping them to different regions. So this is what usually happens. And again, I'll come back to this in the next lecture, where we talk about protection and isolation between different processes. That was a good question. Could you go over execution stack? Thank you for asking that question. So I'm going to go through the execution stack next lecture. So that, that's pretty much what I have here. So these are slides, as you can see, starting from slide 20 to slide 32, they're about execution stack. So I didn't have a time to talk about execution stack, so I'll talk about the execution stack in the next lecture. Okay, so that's that for today. So thank you for those of you who stick around until now. Sorry we went over time again. And thank you for those of you who are watching this later on the recording of this. Take a good care of yourself, be safe, and talk to you on Thursday. Bye-bye.